Put it down. Thanks. Okay, so there we go. So volcanic activity at the Earth's surface is probably one of the most influential geological phenomena to really generate a strong desire to understand Earth's sort of subterranean magmatic systems. And of course, one way to do this that you will all be very familiar with is to study layered intrusions, which represent the fossilized remnants of these magmatic systems that occasionally become exposed at the Earth's surface by the forces of erosion. However, there's sort of one annoying issue that still plagues petrologists, and that is that we don't really know how accurately the layers that we find in these intrusions, how accurately do they actually reflect what was going on within the melt during the chamber's crystallization and differentiation, or by how much have they actually been modified by post-accumulation processes. And it's this debate has recently become very significant in dealing with the massive magnetitite layers that we find in the upper reaches of South Africa's Bushveld complex. Now, to understand why, I have to give you sort of a brief overview of some of the history of the previous attempts that have been made to try and resolve the petrogenesis of these rubber enigmatic rock types, and also just because I really enjoy talking about it. But the magnetitite itself is almost completely massive, consists of almost pure titanomagnetite. The silicates are virtually absent. It has this really sharp boundary, usually with an amorphosite below. You can't see it over here, but the upper contact is usually gradational into a plagioclase magnetite cumulate. You can call it magnetite amorphosite. So my story starts in the early 1980s when two researchers from Wits University, Professors Grant Cawthorne and Terence McCovey, they visited this site, the main magnetite layer in the magnetites area, and they collected sort of closely spaced samples along vertical profiles through this layer. Now, as far as I understand, initially they just wanted to check the vanadium, the variation in the vanadium content, but they actually ended up finding something much more interesting. See, when they plotted the chromium concentration, they noticed this really rapid but remarkably regular depletion in the chromium content upwards. And sort of to explain this, they attributed it to various factors. So first is they stated that this is probably a product of fractional crystallization of the magnetitite from a stagnant basal layer of melt. So you have this relatively limited quantity of melt that can quickly be depleted in chromium content, and also to the extremely high partition coefficient of chromium in magnetite. It can vary from 30 to several hundred. It's even a recent publication by Shepard et al. When they find this extremely high value of 2000 in basaltic systems. And they also proposed that to produce this regularity, that the magnetite was probably either crystallizing in situ, or we were dealing with really short settling distances. Anyway, Cawthorne and McCovey probably found what was the first high-resolution indicator of magmatic processes. I think it's a really remarkable discovery. Unfortunately, for the next 40 years or so, it's been largely neglected. But anyway, so the next thing that Cawthorne and McCovey did is they tried to model this upwards depletion of chromium with sort of simple Rayleigh-style fractional crystallization. And what they found is this is actually impossible to do, since initially you have this really strong depletion in chromium, and then it kind of starts to slow down. So it causes this breakaway from the pattern predicted by Rayleigh fractional crystallization. Now, this is a really important observation that I'll get back to in a short while. Now, this whole story with chromium and magnetite got much more interesting when in the following decade, Cawthorne returned to this site, but this time he collected samples laterally along the base of the magnetitite layer. And when he plotted his results using a minimum sample spacing of 50 centimeters, he got this very erratic, but also very dramatic lateral variation in the chromium content. And to try and explain this, he proposed that the magnetite was nucleating and crystallizing sort of on different spots on the magma chamber floor. So he used the analogy of mold growing on cheese. So you can kind of see the magnetite would be the mold, and the cheese would be the amorphosite. So where the magnetite starts nucleating over here, you get a very high chromium concentration. As it grows out laterally, this chromium concentration drops off really quickly. And he termed these structures growth nodes. Anyway, he went on to construct this figure over here. Now, this is a cross-section of the magnetitite layer, and these represent timelines of the growth of the magnetitite layer, sort of the propagation of the solidification front. So, and this is where I came in with my research. I wanted to see if we can actually observe this growth pattern. And thankfully, since the 1990s, we've seen the advent of much more accurate portable X-ray spectrometers. We could actually map out the chemistry of magnetitite directly on the field, which I did on this grid pattern, much improved sample spacing of 4 centimeters. See if we can reproduce this. And back then, I mean, you also would have seen this at the 2018 Platinum Symposium, if you were there, but we were really delighted when we got this picture and we found some of these. We had found these dome-shaped chromium-rich structures, and we were also really happy to agree with Grant Colfun that they represent in situ growth structures. So we also went on and applied this technique on sort of different outcrops. I think this was the probably the most interesting one. This is the lowermost magnetitite layer in the western limb. This is from the Vametco vanadium mine. Now, we believe that these are in situ fragments of amorphosite, sort of left behind after thermochemical erosion, the underlying amorphosite layer. And so when we scan this layer, I mean, isn't that the most beautiful thing you've ever seen? But anyway, we also found some of these dome-shaped chromium-rich structures we're quite happy about. But you can also see the chromium content is very elevated all around these inclusions, which we also interpreted as additional evidence for in situ crystallization, that the magnetite is growing around these inclusions. Anyway, so in summary, I believe that if you're dealing with petrogenesis of upper zone magnetitite layers, there are 2 really important constraints that you need to keep in mind. The first is we have our upwards depletion that cannot be modeled by fractional crystallization alone. So there's been numerous propositions to try and explain how this works. So Colfun McCovey, they had this idea of the stagnant basal melt layer gets depleted in chromium, and you start building up this really big concentration gradient in chromium. So chromium can start diffusing downwards faster, causing the chromium depletion to slow down. Creer and Smart sort of had a similar model. And in our model, we proposed that this is because of frequent magma additions that causes a thickening of a basal melt layer, causing the chrome to slow down. I think the details are not so important for this presentation. And then, of course, we have these chromium-rich structures that have been inferred to be in situ growth structures. Now, the one thing that all these models have in common is they consider that these features arose during the primary accumulation of the magnetitite layer. So it forms as the magnetitite layer is, crystallizing. So this was the case for all the models until very recently, when Yao and Mongol proposed a really fascinating alternative. So what they suggested, get rid of this again. What they suggested is that these features are actually produced by these late-stage chromium-rich intercumulus melts moving upwards. So what happens is they propose the magnetitite layer can form by crystal settling, and then you produce a chromium concentration along this blue line that matches that of fractional crystallization. But then you have these late-stage chromium-rich melts moving up, and they react with the lowermost portion of the magnetitite layer significantly enriching it in chromium. And then you get this breakaway from the pattern predicted by fractional crystallization. And to explain these dome-shaped or bell-shaped, whatever you want to call them, chromium-rich structures, they proposed that we had significant lateral variation in the porosity of the underlying amorphosite layer. So in areas where your porosity is relatively low, you get sort of this greater flux of chromium-rich melt coming from below, so that after a few decades, you can start producing sort of similar structures to what we see in the magnetitite over here. So at the time of Johan Mangel's publication, they made this really important statement that with the current data, we cannot really tell for sure which of these models are correct. They favored their own model because they said it's simpler than ours. But anyway, so I wanted to go out and collect more data and see if I could actually figure out what is the case. So I wanted to test this intercumulus melt model against 4 predictions, which I believe is a consequence of their model. Now, the first prediction states that if we had some kind of impermeable barrier underneath a magnetitite layer, say like a xenolith, it could shield the upper magnetitite from reaction with these chromium-rich melts, so that the magnetite here might have a much lower chromium concentration than the magnetitite sitting in the normal profile that was sort of free to react with these chromium-rich melts. Now, thankfully, this type of situation is exactly what we have once again at magnetite. Unfortunately, it's extremely difficult to show on a single photograph because of the lack of contrast between the rocks and all the vegetation. But over here, we have the main magnetite layer. It's overlain by the magnetite and amorphosite. And over here, you have a really big basaltic xenolith. We think it's probably related to the Dahlstrom formation. Maybe it was part of the roof of the Bushveld chamber that sort of became dislodged, sank out, and settled on the magnetite and amorphosite. And then magnetitite layer 1, which is the first magnetitite layer we find above the main magnetite layer, crystallized all over this xenolith. Now, Cawthorne and Street, they already had this idea that the xenolith could have served as a barrier to sort of late-stage fluids or melt migrating from below. And they found some evidence for that, sort of that the amorphosite underneath the xenolith was enriched in potassium, also some other things. So anyway, what we did is we collected a samples through a profile of the magnetitite where it's sitting on top of the xenolith, and another of the same layer where it's sort of sitting in the normal profile. And so that's the results we found over there. You still see this really nice upwards depletion in chromium. So now remember, this sample, we would expect it to be mostly shielded from reaction with chromium-rich melts. So if that was the case, we should expect it to have quite a lower chromium concentration than this profile over here. However, what we see in reality is 2 very similar profiles. At least to me, there's not really any sign of relative enrichment or depletion in any of these chromatite layers, which to me would suggest that we do not have a reaction with late-stage liquids altering the chromium concentration of this layer. Now, the second really important prediction states that if we really had chromium-rich liquids underneath these magnetitite layers, we should expect, if we can find cumulus magnetite in the underlying layer, it should have a chromium content that's at least as high as the base of the magnetitite layer. So once again, we took another sample here from underneath the xenolith. This magnetite and amorphosite contains what I would say is clearly looks like cumulus magnetite. It's got about 20% magnetite. So, and here's our profiles for the magnetitite again. So if we really had chromium-rich melts coming from below, we should expect the cumulus magnetite here to have a concentration that's comparable to what we see over there. However, what we see in reality is that the chromium concentration is actually very low, and it looks like we have quite a big chromium reversal associated with magnetitite layer 1. which to me, which suggests that we actually never had chromium-rich intercumulus melts underneath magnetitite layer 1. And I'm happy to see Moose agrees. Okay, anyway. And this leads me to my third prediction. If we do not have chromium-rich intercumulus melts, damn, that takes long to say, underneath magnetitite layer 1, we should not expect to find any of these chromium-rich dome-shaped structures. If they do indeed arise by this reaction. So we applied the same method again, mapped out the geochemistry of magnetitite layer 1, and I mean, there it was, a dome-shaped chromium-rich structure. So to me, that would suggest that these structures actually do not form with reaction with chromium-rich melts. Okay, and now for my favorite one, final prediction, number 4. So this is, once again, this is that same layer I've showed you previously. This is from the Roven vanadium mine in Westerland. And I've said before that the bottom contact between the magnetitite and the anorthosite is really sharp. But of course, if you take a closer look, you actually see many irregularities, so kind of a lot of stuff going on. But one thing you see are these little, sort of really small magnetitite protrusions going into the anorthosite. Now, the prediction here is, if we had chromium-rich melts moving upwards from below, I would expect these protrusions to be most susceptible to reactions, since they don't have any magnetite around them to kind of compete for chromium. So I would expect them to be really rich in chromium. So we analyzed this little protrusion on the left with the microprobe. And I think we actually found something that's kind of unexpected, but really interesting. So what we see looks like some kind of basal reversal. We don't see what we've always been seeing with these magnetitite layers. We see the chromium content are actually increases from the bottom upwards. And this is sort of, so the protrusions themselves are quite low in chromium compared to the overlying magnetitite. And I think, I don't really know why, but I think this is because of crystallization, in situ crystallization of magnetitite into a pretty confined space. So the communication with the overlying liquid is maybe not that good. So chromium is quickly consumed down below, giving you a low chromium concentration. As you move up, perhaps communication with the overlying sort of main magma body becomes better and you get this increase. This is that second protrusion. So once again, we see this, it looks like a basal reversal. Chromium decreases because of what I think is a lack of proper communication with the overlying liquid, but at some point we start seeing this depletion in chromium, probably of the overlying liquid, and the trend rapidly reverses, and then it continues going down for many tens of centimeters. And this is also, this sort of feature is not what I would expect if we had chromium-rich liquids coming up from below. We should expect the highest chromium concentrations to occur here. Okay, now one argument you can maybe make against this is that, well, what if the flow of these intercumulus melts are sort of channelized and they simply miss these protrusions? So what I want to show you next is, this is one of these chromium-rich domes that we've mapped out in a lot of detail. And if you look at that little portion over there, you can actually see a little protrusion sitting over here underneath this chromium-rich dome. So, I mean, it's been proposed that the dome has been produced by chromium-rich melts moving upwards from below. If that was the case, I would expect this little protrusion to be really, really rich in chromium. So what do we actually see? Well, in reality, the chromium content of that little protrusion is actually much lower than what we see in the overlying dome-shaped structure. And this, at least to me, strongly suggests that these dome-shaped chromium-rich structures do not arise by reaction with chromium-rich intercumulus melts. So in conclusion, at least for the time being, I believe the models that propose a primary origin for these features are still the best way to go. Thank you so much for listening.
Have time for questions? Can you just address the presence of plagioclase within the magnetitite layers? So we have a plagioclase crystals, not boulders, that sometimes look very much aligned, like almost foliated. How do they form?
Well, I guess you're probably aware of the model I proposed for that.
So to propose those forms, I told the unorthodox.
Oh, the.
So, sorry,
I know.
I didn't read that paper recently, so I might have forgotten.
Okay. Yeah. Well, the idea there, it's might take a while to explain, but that you have, yeah. So you do have those upper gradational contacts with laminated plagioclase grains. Now we've sort of analyzed the chromium as well, and you still get this extremely remarkable regular depletion. So to me, that would at least show you didn't really have a mush of magnetite. So I came up with this idea to try and explain an in situ origin for foliated plagioclase, which I know is really controversial. Okay.
Hello, I'm Yao. I think I must to ask you some question, but to be honest, if you read my paper in detail, I will tell that all model I think is okay. Yes, every model is okay, but my James just talk to people is that the post cumulate modification of this magmatic layering cannot be overlooked. This first, the post cumulate. I can imagine that maybe 95% of magmatic formed in situ precipitation, and there's no post cumulated process. This is the first. Second, I think maybe 15 years ago, maybe 14 years ago, the people use the chromium pattern of this magmatic layer to try to tell the story about the magma convection. I think at that time is a very nice job. But after 14 years later, the technical is developed, and now we still use just the chromium pattern to tell all stories about the huge magma chamber. My paper is to talk, we can just jump out of these questions. Yeah, because we can do many modeling to fit in all of the data. Yeah, it just can require another magma intrusion and fit in the following two data, and then another magma intrusion to another four data in this section. But I think it's no need to just use this chromium pattern to tell the whole stories, because we have many things to trace the fluid dynamic or magma dynamic in the system. Yeah, I think another thing is also I talk about my paper is that a simple modeling may be the beautiful modeling. We no need to require so many things, so many parameters to change to fit in the data. This is just an email. I think all things I'm easy to say, I accept. My model cannot explain all of the things in this large layer intrusion. But I just want to say simple model is okay. There is no need to try to do more details, just focus on this. Yeah, that's all. Thank you.
Can I have failed to do it simply. And I don't know, there's so many, yeah. Okay, there's a lot to comment on. I think maybe best.
More two questions, please.
Hi, Willem at the back. Thank you for a very interesting talk. I'm just wondering how far we can really push this spatial use of PXRF. For example, on the last slide you showed there,
yeah,
the little, I forget the term, sorry, the one before that, the little, bit of magnetite that's sticking down into the north side there is what, a centimeter across at best. the PXRF window is about 1 centimeter, and presumably immediately behind that, you know, you've not got the same depth of magnetitite in that little blob as you do in the main reef. My question is it possible that you're seeing a lower chromium value in that little bit at the bottom because you're getting interference with something that's not magnetitite? So you're getting basically a third effect.
No. So the data has been really carefully checked in also titanium vanadium ratios. So we do type of I first check to make sure I'm scanning magnetite, and to get rid of any silicates. Well, actually the only silicate that's really present is plagioclase. I plot a chromium vanadium ratio, and it's a calculation you can do, which you've compared with in-house XRF. So I'm really confident that that's a real value.
Hi, so that was a great talk. The one thing that you didn't actually expand on was if you look at Cawthorne and McCarthy's paper,
Yeah,
they have like reversals and things a little bit higher up, so that they are exactly the same kind of pattern sitting on top of a thick magnetite layer. And I think that also, you can't imagine this stuff going up through and then through the lowest part and into the top, same profile again.
Yeah, I think, Kel, actually, you had an explanation for the reversals, but I can't remember. You didn't.
So that those reversals, I think, are very much orthomagmatic that way.
Okay, yeah. Thanks a lot.
Look, a quick question.
Yeah.
What kind of speed value for chromium into the magnet that they use to produce these trends? Because I think you have 20,000 ppm chromium.
20,000.
In what of was it 2,000?
It could be.
So in one of your maps, I thought. Anyway, what
So.
I think that would require.
So it really depends on how thick the basal mount layer is. If it's really thick, you're going to need a big one. If it's really thin, you're going to need a.
The p-value is published between 20 and whatever 1,000. So
2,000.
It seems to be very variable. Which one did you settle?
Well, for my modeling, I could reproduce. I could accurately model vanadium and chromium for values between 300 and 500 chromium.
I added some things in the new experiments to suggest the partition coefficient about 200. So
could you get back to your prediction 4?
Sorry, which one?
Prediction 4.
Prediction 4.
Yes.
Yeah,
exactly. In the next slide, I think you showed this nice line. What is the material, this red material between the anorthosite and the magnetite?
This material.
What is very pronounced one following on the boundary?
I think it's some of the magnet.
Maybe it's a fluid pathway, and you introduce a fluid is enriched in chromium, and your magnetite is the barrier. So it's not permeable.
If you chop this, this is a surface effect. If you chop it off, it's completely, it's gone. It's like magnetite oxidizing and sort of.
But Bob is a very thin layer. You only see 2D, yeah?
The last question there.
Yeah, hematite.
Is there any possibility that your chrome-rich highs are not due to enrichment in chrome, but actually depletion of non-chrome components?
Depletion. So like we have a chromium pool fluid passing by.
So you got something that's, say, dissolving out more iron such that the chrome is being enriched. Just to be contrary here.
Dissolving out. Okay, but you're going to need a chromium pore liquid for that, right?
Or a vapor.
Okay.
I just, there's something I want to share to you then. I don't know if I have time.
It's because we have now the coffee break.
How do
So
I,
we can continue talking the coffee break. Yeah, you want to.
should I?
Okay.
Please, I'll be back in answer time. It was very annoying for what's earlier when things that came in play. So, really fast.